Imagine the universe in its infancy, a time when everything we know today was compressed into an incredibly small, hot, and dense state. The universe was a far cry from the vast, star-studded expanse we are familiar with. It wasn't the vast, star-studded expanse we know today. Instead, it was a seething, chaotic environment filled with energy and particles in a state of constant interaction. Instead, picture a hot, dense soup of energy and particles. This primordial soup was so hot that atoms couldn't even form yet. The particles were in a state of constant motion, colliding and interacting in a chaotic dance. This primordial soup was so hot that atoms couldn't even form yet. The intense heat prevented electrons from binding to nuclei, making the formation of stable atoms impossible. Light couldn't travel freely in this chaotic environment. The universe was opaque, with photons constantly colliding with the dense sea of charged particles, unable to move far before being scattered. Photons, the particles of light, constantly bounced off the dense sea of charged particles. This constant scattering kept the universe in a state of glowing opacity, much like a fog-filled room where light is diffused in all directions. The universe was like a fog-filled room, opaque and glowing with intense energy. This fog was not like any ordinary fog. It was a seething, energetic plasma that filled the cosmos. Then, around 380,000 years after the Big Bang, something incredible happened. The universe began to cool, and this cooling allowed for a significant transformation. The universe cooled enough for atoms to form. Electrons could finally combine with protons to create neutral hydrogen atoms, marking the end of the universe's opaque phase. This event, known as recombination, marked a profound change. It was a pivotal moment in the history of the cosmos, as the formation of neutral atoms allowed the universe to become transparent. As electrons settled into their orbits around atomic nuclei, the fog began to lift. The universe transitioned from an opaque, glowing plasma to a clear, transparent space. Photons were finally free to travel across the universe. This newfound freedom allowed light to traverse vast distances, illuminating the cosmos in a way that had never been possible before. This first light, released from the grip of the early universe, still bathes the cosmos today. Known as the cosmic microwave background, it is a faint glow that fills the universe, a remnant of that transformative era when the universe first became transparent. This ancient light is what we now call the cosmic microwave background, or CMB for short. Discovered in 1965 by Arno Penzias and Robert Wilson, this faint glow is a relic from the early universe, a snapshot of the cosmos when it was just 380,000 years old. The CMB is a crucial piece of evidence supporting the Big Bang theory, providing a glimpse into the conditions of the universe shortly after its inception. It's a faint afterglow of the Big Bang, a remnant of the intense heat that once filled the universe. As the universe expanded and cooled, this heat left behind a thermal imprint, a cosmic fingerprint that we can still detect today. A thermal echo that whispers tales of the universe's earliest moments. The CMB is like a time capsule, preserving the state of the universe at a time when it was a hot, dense plasma. This radiation has traveled through space for over 13 billion years, carrying with it the story of the universe's infancy. But this isn't just any light. The CMB is unique because it is the oldest light we can observe, a direct link to the universe's origin. Unlike the light from stars or galaxies, which has been emitted relatively recently in cosmic terms, the CMB comes from a time when the universe was still in its formative stages. The CMB isn't like the light from stars or galaxies. It's a special kind of radiation that fills the entire universe, a uniform glow that can be detected in every direction. This omnipresent radiation provides a backdrop against which all other cosmic phenomena are set. It's a special kind of radiation, a faint glow of microwaves coming from every direction in the sky. This microwave radiation is incredibly uniform, with tiny fluctuations that reveal the seeds of all future structure in the universe, from galaxies to clusters of galaxies. A faint glow of microwaves coming from every direction in the sky, the CMB is like a cosmic wallpaper, a backdrop that tells the story of the universe's early days. These microwaves are the cooled remnants of the hot plasma that once filled the universe, now stretched and cooled by the expansion of space. Think of it like the heat radiating from a freshly baked loaf of bread. Just as the bread cools and the heat dissipates, the universe has cooled over billions of years, but the warmth of the Big Bang still lingers in the form of the CMB. Even as the bread cools, the warmth persists. Similarly, the CMB is the lingering warmth of the Big Bang, stretched out by the expansion of the universe. This stretching has cooled the radiation to just 2.7 degrees above absolute zero, but it still carries the imprint of the early universe. Similarly, the CMB is the lingering warmth of the Big Bang, stretched out by the expansion of the universe. This faint glow, though invisible to our eyes, holds the secrets to the universe's birth and evolution. By studying the CMB, scientists can learn about the conditions of the early universe and how it has evolved over billions of years. This faint glow, though invisible to our eyes, is a treasure trove of information. It contains subtle variations in temperature and density that reveal the initial conditions of the universe. These variations are the seeds from which all cosmic structures, including galaxies and clusters of galaxies, have grown. It holds the secrets to the universe's birth and evolution. By studying the CMB, we can piece together the story of how our universe came to be. This ancient light provides a direct link to the past, allowing us to understand the processes that shaped the cosmos. By studying the CMB, we can piece together the story of how our universe came to be. Scientists analyze the data from the CMB to uncover the mysteries of the early universe, from the formation of the first atoms to the development of large-scale structures. This research helps us understand not only where we come from, but also the fundamental laws that govern the cosmos. The discovery of the cosmic microwave background, or CMB, was a serendipitous event that changed our understanding of the universe forever. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in New Jersey. They were not searching for anything extraordinary, just trying to map the radio waves emitted by our Milky Way galaxy. Using a large, horn-shaped antenna, they aimed to study the radio waves from various celestial sources. This antenna, originally designed for satellite communication, was repurposed for their astronomical observations. However, no matter where they pointed their antenna, they encountered an unexpected problem. A persistent hum, a background noise, was interfering with their measurements. This hum was unlike anything they had encountered before. Initially, they suspected that the noise might be due to some local interference. Perhaps it was caused by pigeons roosting inside the antenna, leaving droppings that could affect the equipment's sensitivity. Determined to solve the mystery, Penzias and Wilson went to great lengths. They evicted the pigeons and meticulously cleaned the antenna, removing all traces of the birds and their droppings. But despite their efforts, the hum persisted. The scientists were baffled. The mysterious signal continued to be detected, regardless of the direction in which the antenna was pointed. It was omnipresent, coming from every part of the sky, both day and night, throughout the year. This persistent signal seemed to be a constant feature of the universe itself. It was as if the universe was whispering a secret, a faint but omnipresent hum that had been there all along, waiting to be discovered. What Penzias and Wilson had stumbled upon was not mere noise. It was the cosmic microwave background radiation, the afterglow of the Big Bang. This faint whisper was the oldest light in the universe, a remnant from the time when the universe was just 380,000 years old. Their groundbreaking discovery, initially met with skepticism, would eventually earn them the Nobel Prize in Physics in 1978. This accolade was a testament to the significance of their accidental yet monumental find. Penzias and Wilson had inadvertently provided the first direct evidence for the Big Bang theory, forever altering our understanding of the universe's origins and its evolution. Their discovery marked a pivotal moment in the field of cosmology, opening new avenues for exploring the cosmos. Since its discovery, scientists have launched numerous missions to study the CMB in detail. These missions, like COBE, WMAP, and Planck, have provided increasingly precise maps of this ancient light. These maps aren't just pretty pictures. They reveal tiny temperature fluctuations in the CMB, variations of just a few millionths of a degree. These fluctuations, like wrinkles in the fabric of space-time, are the seeds of the structures we see in the universe today. These tiny temperature differences reflect the density variations in the early universe. Over billions of years, gravity amplified these differences, pulling matter together to form stars, galaxies, and galaxy clusters. Section 5. The curious case of the cold spot. While the CMB is remarkably uniform, it's not perfectly smooth. One particularly intriguing anomaly is a region in the southern hemisphere known as the cold spot. This region is significantly colder than its surroundings, much colder than predicted by standard cosmological models. Its existence has puzzled scientists since its discovery. Several explanations have been proposed, ranging from statistical flukes to the presence of exotic particles or even the influence of parallel universes. However, the mystery of the cold spot remains unsolved. Section 6, Wrinkles in Time, Whispers of Creation. The CMB is a treasure trove of information about the early universe. By studying its properties, we can determine the universe's age, composition, and geometry. We've learned that the universe is about 13.8 billion years old and composed mostly of dark energy and dark matter, mysterious substances we don't yet fully understand. The CMB also provides clues about inflation, a period of rapid expansion in the first fraction of a second after the Big Bang. Inflation theory explains why the universe is so uniform on large scales, and why it has the properties we observe. Section 7, The Quest for the Cosmic Code. Scientists are constantly searching for subtle patterns within the CMB, hoping to unlock even deeper secrets of the universe. One such quest is the search for primordial gravitational waves. These waves, ripples in the fabric of space-time, are predicted by inflation theory. Detecting them would provide direct evidence for inflation and give us a glimpse into the universe's first moments. The search for these faint echoes is like listening for a whisper in a hurricane, but if we succeed, it would revolutionize our understanding of the cosmos. Section 8, A Window to the First Moments. The cosmic microwave background is a window to a time when the universe was young and full of possibilities. It's a faint but persistent reminder of our cosmic origins, a time when the universe was a sea of light and energy. By continuing to study the CMB, we're not just unraveling the mysteries of the universe's past, we're also gaining a deeper understanding of our place in the cosmos. Section 9, Our Cosmic Address, The Afterglow of Creation. We live in a universe shaped by the events of its earliest moments. The galaxies, stars, and planets around us, even we ourselves, are all products of the conditions present in that primordial soup. The cosmic microwave background is more than just a scientific curiosity. It's a cosmic time capsule, a message from the dawn of time that carries the secrets of our universe's birth and evolution. As we continue to listen to its faint whispers, we'll undoubtedly uncover even more wonders of the cosmos. For now, let us marvel at the fact that we can witness the afterglow of creation, a faint but persistent reminder of our cosmic origins.